Why is this a useful result? Why is this perhaps handier than some of the things that we've been doing? Yeah.
We don't have to go through 3 blackboards of math to get an answer.
Well, he says we don't have to go through 3 blackboards of math to get an answer. Okay. An answer to what? What question can we now answer simply? Yeah, so if we want to know, well, what was the final velocity, or even what's the change in the velocity, this is going to be a really quick way to go. Suppose instead you wanted to know, well, how long is it going to take? Are we screwed? Does this help? Okay, all right. So if we wanted to find out how long it takes to go down, how would we do it? Integrate what? Yeah?
I would just say find the final velocity and plug it into your velocity equation.
She says find the final velocity and plug it into my velocity equation to get t. Oh, I see. That would work for the straight slope. Would that work if I make it curved? Yeah, maybe not. Imagine I do something crazy, like have it come down and then get flat for a while. Do you see how that's going to like arbitrarily lengthen the time that it takes to get down a certain ways? Yeah. So if I knew the energy, it might be, it could be really handy to deal with what's the final velocity. It might not be so easy to figure out, well, how long is it going to take? Okay. So I want to now see if we can't generalize for an arbitrary shape. And in order to do that, I'm going to carve it up into little bits. So I'm going to consider actually one little bit. The acceleration is dv dt, which is approximately equal to delta v over delta t. That is to say, delta v is about a delta t, and it would be better and better the smaller I make the little time interval. Or delta t is about the change in the velocity divided by the acceleration. So delta t, v final minus v initial for this little interval over the acceleration. How far will it go in that time? Which v should I use? So v final is supposed to differ a little bit from v initial, right? So do I use v initial, v final, v average? What should I use to figure out how far it goes? Maybe v average. So v naught plus v, why did I do that? V final minus v initial, over 2 times delta t should give me the distance that it travels. So this is v average. Now, if a is a constant, like in this problem, then it doesn't matter how long I take delta t. This will still be good. But if a is changing because the slope is changing, then I'm going to start screwing up if I take a big interval. Does that make sense to people? Because I'm going to have different a's for different intervals. Right? Okay, so let's see here. I know what delta t is, so I have delta x is equal to v final plus v initial over 2 times v final minus v initial over a. Oh, that's interesting. That looks like v final squared minus v initial squared over 2a. Right? Do you smell any rats? Yep. Okay, so what we know and love from high school, if I were to multiply through by 2a, okay, that's true if a is constant. But we already figured out, depending on the slope, what a should be in this case. What should the acceleration be? It should be should be g times the sine of whatever angle is describing that little stretch, right? So where we are up there, we have a little stretch, so we have at the moment some little angle theta, and we have a delta x, which is the distance traveled down the slope. So this is the delta x, that would be theta, and the acceleration would be g sine theta. So g sine theta delta x, so 2g sine theta times delta x is just the height change, delta h. So that is the demonstration that it's general. Okay, as long as I chopped up with infinitesimal little bits, the little change in height produces a little change in v squared.